Multi-agent AI is quickly becoming one of the most exciting areas in modern AI systems. Instead of a single model doing everything, you have teams of specialized agents that collaborate, coordinate, and sometimes even negotiate to solve complex tasks. If you are preparing for a Gen AI or agentic AI interviews, it's crucial to understand how these agents work together. In this video, we will cover six core questions. What's multi-agent collaboration? What's the supervisor worker pattern? What's the planner executor pattern? What is agent communication? How do agents avoid conflicts? What is multi-agent deadlock? We will keep everything visual and practical so you can explain these ideas confidently in any interviews. Let's start with the big picture multi-agent collaboration. Multi-agent collaboration is what happens when several autonomous agents work together in a shared environment to achieve a goal that would be difficult or slow for a single agent. You can think of it like a digital project team. One agent might specialize in research, another in data analysis, another in planning, another in execution. These agents coordinate using communication protocols and shared state. They exchange information, divide work, distribute resources, and synchronize their actions. Collaboration can be explicit through message passing and structured protocols, or implicit by modifying a shared environment, like updating a task board or a state store. Why do we use multi-agent collaborations? It scales better for large, complex problems. It allows specialization. Each agent can be optimized for a narrow role. It creates resilience. If one agent fails, another can compensate. Multi-agent collaboration is a pattern where multiple specialized agents share information and coordinate actions to solve complex tasks similar to a well-coordinated human team. Now that we have seen how agents collaborate in general, let's look at a common architecture for organizing them, the supervisor worker pattern. The supervisor worker pattern is one of the most widely used architectures in multi-agent orchestration. In this pattern, you have a supervisor agent at the top, multiple worker agents underneath. The supervisor's responsibilities includes understanding the overall goal, breaking it into subtasks, deciding which worker should handle each subtask, tracking progresses, and combining the result into a final answer. Each worker agent has its own tools, instructions, and sometimes its own model, focuses on a specific type of task, and reports back a status and result to the supervisor. For example, supervisor plan and execute a product launch. Worker 1 market research. Worker 2 drafting content. Worker 3 scheduling campaigns. Worker 4 data analysis after launch. This pattern is powerful because it centralizes coordination in one agent, keeps workers simple and specialized, makes it easier to track and debug multi-step workflows. The supervisor worker pattern is a multi-agent orchestration design where a coordinator agent decomposes complex goals into subtasks, assign them to a specialized worker agents, and then aggregates their outputs. The supervisor worker pattern focuses on who does what. Our next pattern, planner executor, focuses on how goals become concrete actions. The planner executor pattern separates thinking from doing. Here we typically have one planner agent and one or more executor agents. The planner agent receives the high level goal, breaks it into structured tasks, decide task order and dependencies, and determines which tools or data each task needs. The executor agents handle the actual executions, call APIs, run code, query databases, or perform actions in external systems, return structured outputs and status back to the planner. For example, in a healthcare workflow, planner review patient history and suggests follow-up plan. It breaks this into retrieve recent lab reports, summarize treatment notes, check guidelines, draft recommendations. Executor agents then run each pieces, calling EHR systems, summarization models, and guideline databases. The benefit of this pattern is you keep your reasoning and planning logic separate from tool specific execution logic. It becomes easier to swap tools or executors without changing the planning brain. The planner executor pattern divides a multi step task into planning and execution rules. The planner decides what needs to be done, and executors handle how each task is carried out using tools and APIs. Collaboration and planning both depend on one critical capability, agent communication. Let's look at what that means. Agent communication is the backbone of any multi agent system. It's how agents share information, coordinate decisions, negotiate responsibilities, and stay aligned with each other and with humans. Communication usually happens through message passing, structured message with sender, receiver, content, and metadata, and shared protocols or formats so that everyone understands each other. Modern systems often define communication protocols such as the Agent Communication Protocol (ACP), standardized message types like request, response, error, tool call, state update, and JSON-based payloads that are easy for agents to parse and generate. Agent communication can be agent to agent to tool, or agent to human in chat interfaces. In interviews, highlight the need for clear schemas, well-defined roles and channels, logging and traceability, and safety filters on message. A simple way to summarize agent communication is the set of protocols, message formats, and channels that let AI agent exchange state, plan, and result reliably. When agents start communicating and making decisions, disagreements and conflicts can happen. So, how do multi agent systems avoid or resolve conflicts? When multiple agents work together, conflicts are often inevitable. Conflicts can include two agents trying to do the same job, agents making contradictory decisions, disagreements about data, priorities, and policies. Well designed systems use several mechanisms to avoid and resolve conflicts. Clear roles and responsibilities, defining agent role upfront reduces ambiguity about who does what. Less ambiguity means fewer clashes. Standardized communication formats. Clear structured message reduce misunderstanding that might otherwise escalate into disagreements. Explicit disagreement signals. Agents can send a specific disagreement messages such as disagreement detected or a flag in the payload when something looks wrong. Conflict resolution strategies. Systems can implement majority voting, priority rules. Some agents override others. Escalation to a supervisor agent or a human reviewer. Negotiation protocols, logging and traceability. All communications and decisions are logged so that conflicts can be analyzed later and the system improve. Agents avoid conflicts through clear role definitions, standardized communication, explicit disagreement protocols, and configurable resolution strategies like voting or escalation. Even with good conflict resolution, sometimes agents get stuck. That brings up to an important failure mode, multi-agent deadlock. Multi-agent deadlock happens when agents get stuck and the system stops making progress. This can occur when agents wait on each other indefinitely. Every agent is blocked by another's decision. Governance rules or policies conflict and no one can move forward. Multi-agent LLM systems, deadlock might look like agents repeatedly asking each other the same questions, agents refusing to act because of strict rules, or cycles of coordination that never lead to execution. Breaking deadlock usually involves clear governance layers, separating non-negotiable parental rules from more flexible environmental guidelines so agents know what can and can't be changed. Timeouts and watchdogs. Using timeouts or monitoring agents that detect when no progress be, is being made and intervene. Decision overrides. Letting a supervisor agent or a human operator override the loop and force a decision or a reset state. Simplifying interaction patterns. Reducing unnecessary dependencies between agents so fewer circular waits can occur. Multi-agent deadlock is a failure mode where agents block each other and the system stops progressing. We handle it with governance, timeouts, overrides, and carefully design of interaction patterns. Let's summarize what we covered. Multi-agent collaboration, teams of specialized agents working together via shared state and communication. Supervisor worker pattern, a coordinator agent decompose goals and delegates tasks to workers. Planner executor pattern, one agent plans, other agents execute using tools and APIs. Agent communication, structured protocols and message formats that keep agents in sync. Conflict avoidance and resolution, clear rules, standardized messages, disagreement signals, and resolution strategies. Multi agent deadlock, when agents block each other and how governance and overrides restore progresses. These concepts are at the heart of modern multi-agent AI architectures, and they show up frequently in interviews and real-world agentic systems. In these videos, help you understand multi-agent patterns more clearly. Hit like, subscribe for more agentic AI interview content, and share it with someone building agentic AI systems. Thanks for watching, and I will see you in the next video.